What's up? Welcome back. In this episode, you'll see how to solve day 17 for the Advent of Code for 2023. This one is called Clumsy Crucible, and we've got to go through a map and figure out the shortest path with a couple of different twists. The elves are trying to get lava from some lava waterfall into their like machine parts factory or whatever, and the goal is to go from the top left to the bottom right in these crucibles without losing too much heat. And so each of these different blocks represents the amount of heat that we'll lose if we go into and visit that block. So if, for instance, we go here, we're going to lose 4 heat. If we go here, we lose 1 heat. The idea is to get from this top left corner to the bottom right with the minimum loss of heat. So this is like a weighted search, I guess. We're doing like a shortest path where we have weights where we're trying to minimize how much we're spending in terms of heat loss as we go through each one. So let's grab our example input and start messing around here. So let's go into main.rb, and we're going to say our input is equal to this example input. These are like the each city block. So we'll say blocks is equal to input.split on new line, and then we're going to map over that. And for each line, we want to map the line.chars.map to I, and this should give us our blocks. So let's run ruby main.rb, and we get back this nice list of all of our different blocks. Okay, so what I want to do is create a method called find, and the whole job of find will be to find the shortest path through this list. So we'll start with just like the shortest path given the heats. I think it's actually a little easier to work with something smaller, something that's really, really predictable, and also will give us like some interesting data to work with. Okay. So the shortest path through this would be to just follow the ones, right? We want to go across the top and down, and we want to avoid the 9s if we can. Let's just start out implementing shortest path. And then the twist that is involved in the instructions is that the crucible that the elves are moving is a little bit difficult to navigate, and it can move at most 3 blocks in a single direction before it has to turn 90 degrees, either left or right. So later on, we'll have to limit how far we can go in a single direction. But for now, let's just try to figure out the shortest path by following these ones. So this is just going to kind of like limit the scope of what we're trying to solve here. So we'll make a method called find, and this is going to take in some blocks. And our goal with find is to return something here. So let's actually maybe we'll write a little test. And I'm not sure how far we'll get with these tests. It finds the like shortest path or whatever, the shortest. Yeah. So we're not going to count the value for the heat loss for the first one since we start in that tile. Then we want 1, 2, 3, 4, 5, 6 to be our value when we go through this list. So we want this to be 6. And yeah, so then we'll just say blocks is this thing. Should we just do that? Yeah, maybe we should just do 1, 1, 1, 1. Yeah, thank you, Copilot. Okay, so we want that to be equal to 6. So let's run ruby main.rb, and we've got some load error, can't load rspec auto run, gem install rspec. I forgot, I just upgraded to Ruby 3.3.0 because we have a release candidate that will be ready to rock for, I think Christmas Day it comes out for, the next version of Ruby is coming out. Usually it comes out on Christmas. Okay, so we are, let's see, can we run this? Ruby main.rb. All right, so now we have a failing test. Great, so we got nil. This is where things get a little tricky, right? We want to like keep track of all of the states that we're in because we can only go in certain directions. We need to keep track of the states that we're in and what the current heat is at that point. And that will let us know. Yeah. And then we need to like increment the heat as we're going out along the edges of this. And so we're going to kind of like take a little bit of a greedy approach where we want to try to follow the minimum path. So if we're at 1, we'll take 1 and add that to this one. So this like location will end up being worth 2, and this location will end up being worth 10. And then we're going to like take the best of those 2 worlds and try to go down that path. So instead of going down the path with 10, we'll go down the path with 1, but we do need to still consider the path with 10 just in case. So what we want to do is we want to keep track of a few different things. So we want to start with some states, and our states could be some like list of things. So we're going to start off, and this will be our heat. Eventually we want to like optimize based on the heat. So we're going to keep that as our most significant like element here. And then we're going to, in order to be greedy about this, we're going to sort these states and take the smallest one first and explore that. So we want our heat in the beginning, and then we can have our like XY coordinate. We also need to know our direction. So dx and dy. We're starting in the top left, and then there's 2 different states that we can start at. We can either go to the right or we can go down from the beginning. So we can go to the right or we can go down. So that's going to be like our dx and dy. So we're always going to have left, up, or down for our directions that we can potentially go. And then what we want to do is like iterate until the list of states is empty. And we're going to pop off the best state and take a look at it as our current. So we'll say current is states dot. So we need this to be sorted, and we need to remove. So by doing sort bang here, we're sorting in place, and then we're removing an element from the array. So let's take a look at that real quick. So if we have some array of 1, 2, 3, 4, 1, 5, 6, 1, something. Okay. So if we do a.sort, that gives us back a new array. But if we look at A, this is still unsorted. So A is still unsorted. So if we do like a.sort.shift, this will pop one off of the new temporarily sorted array. a.sort.object ID is that, and a.object ID is this. So they're 2 different things. So if we do a.sort bang.object ID, we should get the same object ID as if we had A. So by doing bang, we're sorting in place, and we get back the same array. So now if we do a.sort, well, let's get a new one. So A is this list. Now if we do a.sort bang.shift, now we have a sorted list, and when we called shift, it popped the one off of the front. So we would have had 3 ones, right? And so, yeah, so we need to use sort bang to sort in place so that when we shift, we're removing a state from this list. If we don't use the bang, then states will never be empty. Okay. So that's going to be our current state. Now we can destructure current into heat x, y, dx, and dy if we want. And then we want to also keep track of which states we visited. My kids do this. They're like, oh, I've been to Virginia, and now I've been to Nevada and Oregon and whatever. So we're going to see which states we visited, and this will be set.new. And so we need to require set, I think. And then we'll say something like, if we've visited this state, and in this case, the state is going to be everything in current except the heat. So x, y, dx, and dy. So if we've visited that state and we're headed in a certain direction, then we know we have already visited it. Otherwise, we want to add that into our list of visited. Okay. That we don't want to include the heat there, because otherwise, every time you visit the state, there's a different heat there, right? Like when you go to Nevada, if you go in the summer, it's hot. It's very hot. If you go in the winter, it's very, very cold. So we don't want to include the heat there this time around. Okay, so what do we got now? Okay, so now the next step is, so this is basically just find the current state and then check if we've already been there. We need to know if we went to the right or if we went down, what would our new x and y be? So let's get a new x and a new y as dx and dy. Okay. We want to check and see if it's inside the grid. If it's not, then we're going to run into issues. And I always use x and y backwards. So our block sizes are a little wonky, but okay. So this is make sure the new X and new Y are on the grid. Now we can get our heat, or like a new heat, right? And our new heat would be the current heat. So this is our current heat, which would be 1 plus what is the heat at that new X or new Y. So when we're looking at this first state, we pop off this first state and we're looking, we haven't visited yet. Now we just visited this first state. And now we have our new X and our new Y. Our new X and our new Y is going to be, in this first case, because we're going to the right, our new heat would be 1. Yeah, our new heat is going to be 1 because our existing heat starts at 0. 0 plus 1, so our new heat is going to be 1. Now what we want to do is check if we've reached the end. Okay, so if we've reached the end, in this case, that just means that we're at like the bottom right corner. If nx is equal to blocks dot minus 1 and ny is equal to blocks dot length, first dot length dot 1, then we want to return that new heat. That means that we're done. We found something. We found it. Yes. Okay. All right, so now we need to add the new potential states. So if we didn't find it, we're not at the bottom right corner. Now we need to keep exploring. The potential directions we can go is left, right, up, and down. So let's make a list of directions we can go. So we can go right, we can go down, we can go left, and we can go up. Okay, so these are all the different directions we can go. Now we want to say dirs.each do direction. We can destructure this into ddx and ddy. I don't know. Or yeah, this is going to be, because we already have a dx in here. So we already have the direction we're changing for the current state. So this is the direction that we would be changing for the next state. Here, what we want to do is we want to check don't go back the way we came. That's good. If ddx plus dx and ddy plus dy is equal to 0. So if we're going to the right and if our direction is right, that would be 0, 1. And then if we tried to go back to the left, we would get 0, -1. 0 plus 0 would be 0, and then 1 plus -1 would be 0. So then we would end up with 0. This would tell us that we're like going back the way that we just came from. So we want to skip over that state. And then I guess for each direction, really, we want to add in some states here. So we want to add our new heat, which was calculated based on expanding around in the directions near us. And we also want to add our new X and new Y. And we want to add the direction that we're going. So this is like the new direction that we're going as we're going through each of these directions. And that should, I don't know, maybe that should get us something like a passing test, maybe? Let's see. Hey, oh my gosh, no way. All right, that's wild. Okay, we found it. All right, cool. Now we want to throw the wrench into the mix. Back to the instructions here. We can move at most 3 blocks in a single direction. Because we're keeping track of the direction we're going, we also need to pass forward how many times we've already stepped in that direction. Yeah, one of the hardest parts of these kind of trick questions is to figure out what you need to pass forward. And so in this case, at each state, we also need to know how many blocks we're passing forward. Blocks in dir? I don't know, blocks in that direction. So here we'll say, okay, so if we were able to go maximum, I guess max in dir, because so this would be like max, the maximum number of blocks that we can go in that direction. For this example, when we run it with 1, it should continue to work and be the number 6 because, or no, I guess we want this to be like 10 or something. If you can go 10 blocks in any direction, then it should be able to navigate through this just fine. For all of our states, we need to add in the concept of how many times we've gone in that direction. And for our starting states, we'll say that we've gone 1 in that direction. This looks crazy, right? Like these a bunch of zeros and ones, but hopefully this makes sense. So we have our heat, we have our dx, we have our dy, and then we have our like num in, or like count in dir or something. Yeah, count in, yeah. That's how many we've gone in that direction. So now when we destructure current, we're going to get count in that direction. And I think we still, yeah, we actually, do we need that for visited? I don't know. We'll have to come back and experiment to see if that's actually required for visited. We need to figure out whether or not we should add the state. And if we're changing directions, then we need to reset the count in the directions back to 1. If we're going in the same direction, we need to increase it. If going the same direction, increase num in, we called it count in dir. Okay, so if those are the same, that means we're going the same direction, then like a new count in dir is going to be count in dir plus 1. Otherwise, the new count in dir is equal to 1. I know this is, hopefully this is easy to follow, but okay, so now we have this other state in here, and our test should theoretically still be passing. Okay, great. Now we can write another test here, and it finds the shortest path without limitation, or okay, and then it finds the shortest path with max 2 in dir or something like that. And so then we have to change this to 2. Okay, so the number is actually going to be different, right? Because we can't just skate across this top row and down this column. Now we need to say, if we've gone 1, 2, now we have to turn. So now we plus, so we're going to have 1, 2 plus 9 is 11, 12, 13, 14. I think that might be right. 14, it might be more than 14. Let's see. Okay, expected 14, but we got 6. Okay, so this means that we are not actually limiting it. So we're counting it, we sure are counting it, but we're not restricting it. So we need to like skip over. Yeah, so if the new count in that direction is bigger than max count, then we need to skip over it. Okay, so if the new count in that direction, so let's say that we're going to the right and we're passing forward this new count to the right. If that new count is bigger than, in our test case, 2, then we should not include it in the list of possible states, the possible next states. All right, great. So now we have another passing test. That's fantastic. Okay. I think we might be ready to test the example input. So let's comment this out for a second. And what we want to do is say p find blocks. And in the example here, it says 3, and we should get back 102 as our answer. So let's run this and see what we get. I got back 6. That's because we left in our other input here. Take that out. Okay, found it, and it is 102. So that matches what our example was. Fantastic. Okay, so let's now drop in our real input. Okay, get your puzzle input. Get your puzzle input. And here we go. 102 still, because we didn't actually use our puzzle input. And here, okay, we need to say, yeah, so we're going to say input is data.read. So we'll just read all the data in and run it. And it's hanging. Okay, so now we need to have a discussion about data structures. Okay, so the couple of things here, right? Works for the example input, fantastic. When we do sort bang, this is expensive. When we do shift bang, this is also expensive, I think, in Ruby. Shift, let's see, big O for shift Ruby. Really, it depends on how shift is implemented under the hood and whether or not it is reallocating a bunch of memory and then moving stuff around? I don't actually know the answer, but I just assume that shift is expensive, but I know for sure that sort is expensive. Big O notation for sort bang in Ruby. I think, yeah, so under the hood, it's using quick sort, which is n log n. And so every single time, for every single state that we go through, we're doing n log n operations to sort it. And then we're doing a shift, which might also potentially be expensive. Let's maybe assume this isn't expensive. This is n log n times the number of states, which is really, really, really expensive. So I actually ran this with the same implementation we have now, and it took 15 minutes and 38 seconds. So long time, but there is another data structure that we can use that is basically perfect for this use case. So anytime that we want to pull off like the minimum one, we can use a heap. So a heap is a special kind of data structure that you can pretend that it always stays sorted. It's not necessarily true, but it has a really efficient way of resorting when items are added. So by staying like mostly in a sorted state, when you pull stuff off, it will give you the minimum pretty efficiently. We want to change states from an array. I'm going to leave in the array implementation just so you can see. This one is like slow, and then current is states dot pop, and here we're going to use a heap. We're going to say heap dot new, and heap is something that you can get from a gem, RB heap, the RB heap gem. So head over to RB heap, RB heap here, Florian's RB heap implementation. So you can initialize it with like a method to call on pairs of objects when it's comparing the sort. You can also pass it a block here as the comparison function, so that when this will be executed when it needs to do its reheaping thing. Okay, so here it tells us that pop is O log n and peak is constant time. When we pop, it removes it from the heap, returns it, and then does its heapify thing. And then if we peak, we're just looking at the top one. So this will be faster, much faster. So we'll get n log n. But if we try to run it like this, so ruby main.rb, then we get an error here. Undefined method less than for instance of array. So before we go too far, let's go back to the example input just so that we're working with a smaller case here. Okay, so we need to figure out how to pass a block to heap so that it can compare our states. Because our states aren't just numbers, it needs to know how to compare those. So let's actually let's play around with heap for a second. Require RB heap. And if we make a new heap and we can say heap, we'll push in 1, and then heap, push in 4, and then we'll push in 2 and 8 and 3, whatever. So we've got a heap and it has a bunch of values in it, right? And you can see the internal instance variable for a heap looks sorted, but it's not necessarily sorted. Also, there is a reference to the proc that's going to be called when it does its comparison, and the default proc is somewhere in this file. So that's cool. So if we do h.pop, then we get back 1, and 1 should no longer be in the heap. So if we look at h again, you won't see 1 in the heap here. And interestingly, like the last time that we saw this heap, 3 was at the very end, right? And it was like, heap doesn't look like it's actually sorted, because we have 1, and then we have 2, and then another 2, and then an 8. But you would think that 3 and 4 would be on the other side. So the internal representation looks like array-ish, but really it's being stored as like a tree, and every time that we pop something off, it gets reheaped or reheapified. So in this case, like right after we did h.pop, this caused an operation which moved the 3 from back here until between the 2 and the 8. So now this is like more heapified. So if we do h.pop again, we get back 2, then a 2, then a 3. Now, what would you expect the next value to be? Okay, we just popped off 2, 2, 3. That was 2, 2, 3. Is it going to be an 8 or is it going to be a 4? What do you think? It should give us the 4 because when we reheapified by calling pop, 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 this heapify, heapify, heapify. And at one of these different points, the 4 got moved in front of the 8, surely. So if we look at H, now we have the 4 in front of the 8. So if we do H.pop, we're going to see the 4. The other thing is let's put some more back onto it. Let's put on 10 and H, we'll put on 1 again and 1 again and 1 again and 1 again and 1 again. As you are shifting stuff on, you can see it like moving around. What's interesting is you can also put negative numbers. And if we do H.peak, this will tell us what the front one is, but it won't actually remove it. So if we look at H again, it's still there. So H.peak is a way of looking at the front without popping it off. Okay. All right. So we're going to create a new heap. And this time we want to pass in a block that will compare array values so that the contents of our heap, the elements of our heap can be arrays. So let's just like start actually by looking at array of 1, 2, 3 and an array of 1, 1, 1. Is A less than B? Oh, we get the same error, right? We can't have a less than. But oddly, you can do like A rocket ship B, which tells you that A is bigger than B, right? We looked at this comparison operator a few episodes back. So if you want to look at rocket ship stuff, you can go look at the comparison. So if A rocket ship B is 1 and B rocket ship A is -1, that means that B is less than A. What we can do is we can use this information as part of heap.new when we pass in this block of A. So when we compare A and B, this block is our comparator. And we want to say if A rocket ship B is like equal to -1, then it's like correctly sorted in the right order. So now if we say H and we push on 1, 2, 3, and then we push on 1, 1, 1, and then if we push on 1, 2, 1, and just for fun, we'll put some 10s in here. Okay, and we can also do some negative numbers. All right, so H.peak gives us back the minimum array correctly. So we're expecting these to be in order based on their first element. If their first element matches, we want to look at the second element. So if we do H.pop, and now we have, so H.pop should give us 1, 1, 1. That's like the next smallest. And then 1, 1, 2 and 1, 2, 1, we want to get back 1, 2, 1, right? Because that is smaller. In our representation, this means the array is smaller, and we want to investigate this state next because that means that we have, potentially a smaller path. So H.pop again, and we get 1, 2, 1. So that's correct. So we would end up like exploring all of those different states in the order that we want. So we need to pass this a comparator, and our comparator is going to be A rocket ship B is equal to -1. And by doing that, when we call pop here, it should be pretty fast. So yeah, look at this. It's still hanging. That's because it's only been running for a few minutes. So let's run it again over here. It'll be a race. It'll be a race. Okay, boom, found 102. Now we want to run it against our real input. All right, cross your fingers. Hey, look at that. Okay, so we got back 1110, which is our puzzle answer for part 1. Okay, so that is the answer for part 1, and it ran in a reasonable amount of time, right? 5 seconds. Not too shabby. Not too shabby at all. Oh, hey, real quick, a shameless plug. Buildandlearn.dev. This is a podcast where me and my buddy Colin hang out and we talk about software development and also just things that we're building and we're learning. So if that kind of stuff interests you, head over to buildandlearn.dev. You can listen on any of the podcast players that you're used to. So yeah, let's get back into advent code. Cheers. On to part 2. So the crucibles of lava aren't large enough. So now we're going to use ultra crucibles. And the ultra crucible introduces a new restriction where it needs to move a minimum of 4 blocks and then a maximum of 10 consecutive blocks. So before our max was 3, but now we're going to have a max of 10. And a new constraint here is a minimum of 4. So we are still passing forward our count in direction. I think we can just modify this restriction here. So if the new count is greater than max in the direction, or the new count in dir is less than the min in dir. And then I guess we have to take in a min in dir. Let's see. Min in dir, max in dir, dir. So for the example use case, it was 1 and 3. And if we run that again, we still get the same answer. That's good. All right. So now we want to run this against 4 as our minimum and 10 as our maximum. I'm going to stop printing out the blocks too, just so that we can see. Oh, let's also run it against the example because then we can compare. All right, we got nil. That's not good. All right, so we have our input where our minimum is 4 and our maximum is 10. Oh, I guess it's going to be below the minimum. Yeah, it's going to be below the minimum in the beginning no matter what, right? Because we've only gone 1. We do need to collect up the first few states. I think this condition, we only want to check this condition if we're changing direction. Like if we're making a turn, that's when we want to check if this is different. So we need to kind of like combine whether yeah, okay, so here we have we'll say turn is true and turn is false. And here we can say if turn and that, then we want to skip it. Okay, so we're expecting 94. We're looking for 94 here. Okay. So, okay. So if we're making a turn, so let's say, okay, so we are making a turn, but every time we turn, we're resetting the new count back to 1. So I don't think we want to, we don't want to check against new count. We want to check against the count for the current state, right? So let's pull that out and take a look here. 94, that is the example. Okay, so now let's run it against our input. All right, 1294. Is that the answer? 1294. That is the answer for part 2. Oh my goodness. Okay, that's pretty cool. All right, so we've got this working, and yeah, I think this makes a little bit of sense. Again, yeah, if you're using just like the default arrays and such, you might be needing to do something very fancy to keep this fast enough in any language, really, so that it can go through and process these as expected. Now, what I'm not sure about is if visited actually needs to have the count in that direction. If we pull that out, I'm not sure if that matters. Let's also run this against the example input here. Okay, yeah, it does matter. Because yeah, it's technically a different state then, right? If we encounter that same tile but with a different number of counts of that direction. Okay, so we've got our 94 back. Is there anything else that we could trim off here? I am not sure. I guess if we are doing a turn, this is where we could check to see if the count is less than min in dir next. And then we don't have to keep these variables around. Well, I guess if the count in that direction is not that, then we could do that early. Okay, that works. And yeah, okay. Yeah, I'm pretty happy with this solution. I learned a lot about heaps. Yeah, it's been a long time since I've messed around with heaps. So it was fun to pull out RB heap, this library that was already written for us to play around with. How do we keep a basically like priority queue so that we can work through this in order? Thanks so much for watching. Really appreciate your time and attention, and we'll see you in the next one. Cheers.